This lesson is on the photoelectric effect, and I have the basic idea shown here in the diagram. So this is the surface of a metal, and the idea is electromagnetic radiation strikes the surface, and the energy from the radiation is transferred to the electrons in the surface, and these electrons move off as a result. The formal definition is given here as well. So the photoelectric effect is the emission of electrons from the surface of a metal by electromagnetic radiation of a suitable frequency. Now, the word suitable here is key, because if you look at the spectrum down here, the frequency increases as you move from left to right through infrared, visible, ultraviolet, and so on. And it turns out that the more the frequency, the higher the frequency, the more likely it is for the electrons to be released in a particular metal. Now we must set some historical context as well. It was accepted by scientists in the early 1900s that light traveled in waves. Now, when I say light, I mean visible or invisible light. In other words, the whole electromagnetic spectrum. And so it had been proven by experiment at this stage that light travelled in waves. However, the wave model of light caused a problem when trying to explain the photoelectric effect, as we're going to see shortly. And it was Einstein who finally resolved this problem in 1905 with his paper on the photoelectric effect, which said to consider light more as particles instead of waves, particles of energy. And for this work, he was awarded the Nobel Prize in Physics in 1921. So on this slide, I'm going to outline, first of all, what the problems were with the traditional model of light as a wave. So I have light represented as a wave on the left here, and then I'm going to outline the solution that Einstein proposed on the right here, where light is considered as particles, as I've shown here. We're going to make this example as concrete as possible. So to do this, I have drawn the surface of a piece of metal here. And if we consider just 4 electrons on that surface for the moment, these 4 electrons, and we just consider what happens to them in different situations. And before we do that as well, we have to also define this concept called work function. Now, work function is a property of electrons. It's given the Greek letter phi as a symbol. And the work function is basically the amount of energy the electron needs to break free from the metal. So there's a fixed amount of energy that the electron needs to break free, and that's called the work function. Okay, so starting with our model of light, as a wave. Imagine some visible light, for example, a simple torch or something like that, you're shining this light on the surface of the metal, and the electrons don't move off in this first example. So they're obviously not getting the energy from the light to move off. So common sense would dictate at this stage that if you increase the energy, they might finally move off, and that's what scientists did at the time in the early 1900s. They increased the energy, which is the equivalent of increasing the amplitude of the wave in this direction. So that's basically shining a brighter light on the metal. But even with this extra energy, they found that the electrons still wouldn't move off. So this was a puzzle at the time to scientists. Now, the next thing they did was moved on to ultraviolet light, which is a higher frequency light. And they found out that finally, maybe for a particular metal, things started to happen, electrons started to move off. But again, there was some puzzles here. For example, 2 electrons might move off and 2 more might stay behind, in my particular example, where we consider just 4 electrons. And then by increasing the energy, they found that all electrons finally moved off. Then they increased the frequency again, finally, for something like X-rays, which has a higher frequency again. And they found out that in the first example, 2 electrons might move off at high speed. So this time it's a higher speed than in the case of ultraviolet. And again, this couldn't really be explained. When they increased the amplitude, all 4 moved off at high speed. So the only difference here between this and the ultraviolet situation was the frequency of the light. So now we go back to the start, and we go over to Einstein's explanation of what's actually happening here on the right. So the first thing Einstein said was to consider light as a series of particles of energy, these particles here, instead of as a wave for the moment, and just see where this gets us. And also he said, if you take the frequency of the wave, whatever it is, in this case visible light, the energy in each little particle, which he called photons, the energy in each photon is hf, where h is a constant. And that constant is known as Planck's constant. It's called after the German physicist Max Planck. So this was Einstein's idea that light traveled in particles of energy called photons. And the energy of the photon was proportional to the frequency of the light. And the constant of proportionality, as we'll say, is h, Planck's constant. Now, if we go with these models and see if it makes more sense this way, Einstein also said that each photon, each particle of light, matches up in a one-to-one correspondence with one electron. So, for example, this HF here might match up with this electron here. And then he said the reason why the electron doesn't move off in this first example is because the energy in the photon simply isn't high enough. So you need this minimum amount of energy called the work function for the electron to break free. And Einstein said that the energy HF in this first example simply wasn't high enough because the frequency was too low. Then if you increase the amplitude in the traditional model of the wave, Einstein said that's the equivalent of actually just increasing the overall energy by having more photons, but each individual photon, and this is the key, each individual photon has the same amount of energy as before. And as a result, nothing still happens, because if they all still have the same energy, well, this HF is still not high enough to displace this electron here, because HF is still lower than the work function. Then moving on to ultraviolet light. So we considered Einstein's model again. So now the frequency is higher in the case of ultraviolet. So in Einstein's model, this corresponds to if F is higher, that means the energy of each photon is higher as well. So at this stage, it might mean that the frequency is finally high enough and the energy of the photon to displace an electron. And this is what happens in my example here. These two photons are going to match up one-to-one with these two electrons, and they're going to be displaced because the energy is finally at least as high as the work function phi. Then when you increase the amplitude, in the old model, that's the amplitude of the wave. Well, again, Einstein said that's the same thing as increasing the number of photons. And each photon now has higher energy as well. And each of these photons now can displace an electron. So the 4 electrons move off. And finally, if you increase your frequency even further, up to something like X-rays, for example, well, now F is higher, which means the energy in each photon is even higher again, which means now they have more than enough energy to displace an electron. And that's what happens. Each photon matches up one-to-one with an electron over here, and they move off at even higher speed because now they've got excess energy, and that goes into kinetic energy as speed. And if you increase the amplitude for one last time, that's again the equivalent of having more photons, and each photon now has more than enough energy, so each photon will displace an electron, so the 4 electrons move off with energy to spare, and they move off therefore at high speed. All of this photoelectric effect can be summed up really in one equation, Einstein's photoelectric equation, or Einstein's photoelectric law. And what the law says is that the energy from a photon is released and given to an electron, and it's broken into 2 bundles as such. One bundle of energy is the energy needed to make the electron break free. That's the work function here. And the remainder of the energy goes into kinetic energy, which is the electron moving off at speed, half mv squared here. That's often called Vmax. They take the speed of the maximum electron moving off, the maximum speed of an electron moving off. So that's it. Einstein's photoelectric law, energy from a photon is equal to the energy to release an electron plus the kinetic energy of an electron. HF equals work function plus a half mv squared.